and trying to use that within software engineering. And the last part is how would we try and use these ideas in adaptive systems? So the goal might be to build a system or evolve a system which is capable of learning over a long time. And for doing that, we might want what I called a shallow architecture. So instead of being composed of a single monolithic structure, a single tree, we might want something more like a mangrove swamp full of tiny little trees that interact. So the point of being shallow is information has less distance to travel before it reaches some point where information. I'm going to argue that that's in practice going to be essential for anything that we want to build that's adaptive over the long term. So a little bit about genetic programming. A few years ago, we celebrated the 30th anniversary of John Coase's first book. I produced a little paper going very briefly over the history of GP. And one of the comments was, well, this is the academic history. What has happened in industry? And the short answer is, I don't know. I don't think anybody knows. And for two very good reasons. One, in industry, there's no incentive to publish. And the other one is there's actually a very strong incentive in some cases to keep what you're doing secret. We had a keynote from David Andre, who was a PhD student, has a thesis in GP, went to Wall Street. He spent probably about 20 years on Wall Street. And he said, the one thing you cannot do is let the opposition know what you're up to. And so he was using GP, no way he was going to go anywhere near publishing. So his work is not in the GP bibliography, which is, for my sins, what I maintain. There's some flares about what bibliography dotted around. But what I did do was to look at what is actually being published. And to me, I was kind of surprised. Something like 38% papers in the bibliography are on GP, but they are on applications. They're not GP. Here's our best ever GP. The target for paper is the application. And so 38% of all the papers on applications. The pie chart tries to break this down. There's a lot of work on medicine, things like trying to predict cancer, interpreting images, particularly X-rays, again, mostly targeting cancer, but a lot of work on image processing. One thing that still surprises me is this large selection we have on civil engineering. And a lot of that is from hydrodynamics. So river flows, water in lakes, oceans, beaches, sometimes deep water. And the last big segment is this yellow materials research. A lot of work on steel industry and sometimes more exotic things like graphene. So just as a comeback, this is not just in books. It is actually, in some cases, out in industry and may have prepared to paper. In terms of creativeness, these aren't all GP, these are all sorts of different GA techniques. I'm just going to talk about one, I think. The one in the middle is a silver coin that was struck by the mint in Portugal 2 years ago. And the design of that 10 euro piece was created by a group in Cumbria, and they used their favorite GA technique for coming up with that wacky design. And that design won Ironically enough, it's a silver coin, and they won the silver prize. So the thrust of the experimental part of the talk is inspired by this work by Richard Lenski. So some 38 years ago, he was on his first postdoc, and he wanted to set up an experiment where he put a bacteria in a flask, kept the environment in the flask very stable, and looked at how that bacteria was going to evolve. And he was told very firmly, there's no point. We know what's going to happen. The bacteria is going to evolve to the conditions, to meet the conditions in the flask, and then evolution will stop. Absolutely simple. No point doing this experiment. 38 years later, that experiment is still running. He has retired. His colleagues are now running this experiment, and the bacteria are still evolving. So their fitness is still increasing. So inspired by that, I thought, well, okay, can we build a GP system that's stable enough to run for a million generations? And then let's see what happens. So this is results up to 100,000 generations. Each of the colors refers to a different run. So you can see there's a lot of variation between the runs. But they all show very strong behavior that fitness improves rapidly at the beginning of the run. This is a log scale, so this is really a lot of time. But over time, they continue to find fitness improvements. Typically several thousand, 1,000 or so fitness improvements during the course of the run. Worryingly, from my point of view, is these lines are tending to flatten off. So although it's still finding improvements, the rate at which improvements are found falls away. This one is it's actually a graph plotted in the Foundations of GP, which I wrote with Ricardo some time ago. What I've plotted is, so these are enormous numbers. This is a log scale. So we're looking at really enormous trees out here. The line I've labeled with full trees is very bushy trees. So we increase the depth by 1, we double the size of the tree. The other extreme is this straight line, which is essentially a very tall, thin tree. So if we add 1 level to the tree, we just add 2 nodes to it. The colored dots are, and colors are different runs, but you can see each of the runs fairly much tends towards this straight line. It's a log-log plot. This is the gradient on there is a half. This is a parabola. And the parabola is where pretty much all the trees are. So there's some nice theories by Philip Paget looking at the distribution of random trees. And they pretty much cluster around that straight line, which is where our GP trees are clustering. So we start off here very small. Over time, the trees get both deeper and bigger. So the explanation for why innovation is falling away, what I've done is each of these dots is an average. So if you look at the raw data, it's smeared all over the place, but if you take averages, you get nice straight lines. What I'm plotting is the reciprocal of the size of the tree against the rate of improvement. And you can see, again, the colors mean different runs. So each one has a different color, but they all end up headed towards the origin. Meaning, if you have an infinite sized tree, it will not innovate. But as I said, worryingly, as we start off down here with smallish trees, we increase the size of our trees, then the rate of innovation falls away. And it falls away pretty much as an inverse parallel. And the explanation from that is the trees converge. They converge so that only the part near the root node is still sensitive. If a crossover hits the outside of the tree, a long way from the root node, most of the time it has no impact. For those who are told that mutations would just break programs all the time, this is totally not true. Most mutations have no impact. I should have stressed, this is a floating point system. I'm going to go on to an integer system. This is another of John Koza's benchmark. It's the Fibonacci sequence. Can you evolve a program, an integer program that's going to generate Fibonacci sequence? I've deliberately chosen one of the solutions that's small enough to put on a graph. This part of the tree all has white nodes, so you can imagine there's a white node. The significance is the red nodes. If I do a minimal change to the execution of the program, so I artificially go in and I zap something, and the minimal change in the integer system is just to add 1, then the red nodes at the top, pretty much I break the program. The red ones mean more than half the test cases you get wrong. The blue nodes mean you get 1 test case wrong. So this is a system with 20 test cases. The blue nodes means you're wrong on these, might be wrong on 5%. The white nodes, you change the execution, it makes no difference. You carry on passing all the test cases. And you can see again, the sensitive part of the tree is up on the outputs. So this is conventional way of doing GP trees upside down, with the at the top. The output from the program pops out. So what I've done here is I've taken a variety of evolved solutions to the Fibonacci sequence, and I've zapped individual components and looked at the impact of them. And where I've zapped is in distance from the root. And you can see this is log scale, pretty much an exponential form. Not only exponential, but fast. So if you go a few levels, you go 2 levels down, your impact is already halved. You go down 30 levels, you're not seeing it. So that's doing a minimal change. This is, I zap the same nodes, but instead of doing the minimal change, I could randomize the execution. I replace the value that's there by a random 32-bit value. And again, we have a pretty good fit to an exponential. So what I'm saying is, unless your mutation, your crossover is near the root node, you're not going to see it. So the next part is a little bit about information theory, trying to justify why this happens. And not only that, but to claim that we should see the same behavior in any hierarchical system. And then we're going to go on and look at the real code, which is not hierarchical, but we see something similar. Is this making sense? I'm getting some people are nodding. Okay, right. So the idea.
Are you going to explain the information theoretic reason for, let's say, information theory says impact disruptions, loss with distance when nested? Is this something you're going to explain?
Yes. of my next task. So going now more into the software engineering world, there's a theory from Boas, which he called the Pi framework. And the idea is for a bug to have impact, not only does it need to exist, but the bug needs to be executed. So a lot of time when you're actually testing things, part of the problem is, can you actually execute the piece of code you're interested in? So I'm going to assume that, yes, we can actually get the critical code executed. From the GP point of view, that's no problem because we know every node in the tree is executed. But in software, complex human-written software, simply generating a test case that executes the bug is often tricky. The second part of this framework is what he called infected. So not only do we need to run the buggy code, but it actually needs to make a difference. It needs to make a difference locally, which he calls infected. And then that difference, whatever it is, that change of state, needs to propagate to the output, which is where the information theory is going to come in. So what we're saying is, from an entropy point of view, from an information point of view, we have a signal which is the bug. Does that signal propagate through the code to the output? And what I'm going to claim is, at least in the simple, purely hierarchical system, the GP system, the chance of that information flowing up the hierarchy to the output falls away the further we are away from the output, the more distance the information is traveled. And we'll see something similar in real code. So the two examples I'm going to be talking about are not pure hierarchies. They are deeply nested code, but they are real code. The first one I'm going to talk about is the BIP system, which is from the NASA Parsec benchmark. The argument really, in terms of information theory, is I put up this, what I'm calling a funnel. Essentially, the idea is all the operations in a conventional computer are not reversible. So here we have a function with two inputs. Here it's just adding together two floating point values. So going into the program, into the funnel, we have at most 2 times 32 bits. So total of up to 64 bits of information going in, but coming out, we've only got one 32-bit answer. So we've only got at most 32 bits of our output. If we start nesting our functions, then we have a situation where if information, because it's purely hierarchical, if we have information that starts at the top of the hierarchy, if at any point in the hierarchy it's lost forever, and the output cannot recover. So the argument is the further we go through the hierarchy, the more chance there is of loss. And we saw in the GP system, essentially on average, we get an exponential fall away. What I'm trying to argue here is if we view the red arrow as introducing some disruption, then we can argue that as we progress through the hierarchy, there's more chance of losing that information as we go. And as I said, it's pure hierarchy, so losing the information can't recover. By losing the information, that means we can't actually see the bug. So I jumped ahead a little bit. So the BIPS benchmark is an image processing thing. Yeah?
Yeah. I'm just talking a bit about the concept of the bug here, because I understand we said part of the sort of the sort of coloring of the key nodes is based on fiddling with the but mutating as it were the data being processed. But I would have thought of something changing in the source code as it were.
Okay, so what I think is nice about this is it's a generic description. So the disruption could be due to a source code bug. So something has injected a signal that shouldn't be there, or it could be, as we'll see in a moment, we could have mutated the code. It could be some sort of hardware glitch. If you imagine we're in some spacecraft, maybe the transistor got zapped by the gamma ray. So it could be any sort of disruption, maybe software, maybe something else. But in a purely hierarchical system, we are at risk of losing that information. And the deeper we are in the hierarchy, the more chance there is of loss. Okay, so let me show you what we've done in experimentally and see if that answers the question. What I'm going to do is I'm going to take this C code, I'm going to use this tool Magpie to mutate it, and then I'm going to look at the impact of those mutations. The first example, I spent some time trying to tune out, so all the code that was not being executed, I tried to remove. So we should have most of our mutations in live code. Didn't actually work, but most of them work. The benchmark, all we're doing here is taking large picture and generating from there. And this runs over, I think, 16 threads. So it's a multi-threaded project. And the definition of impact is if any bit in the output is changed, we regard that test as having failed. So it's a very, very binary thing. Even if it's just one bit of the green that's changed to a different color, we still regard it as having failed. So we take 1,000 mutations, we throw them up in code, and mostly the code just keeps moving. We have a worryingly large 30-odd% where the mutated code didn't compile. Magpie is supposed to produce syntax correct code, but the compiler threw out about 30% of it. In terms of C++, this one's C and the next one's C++. So in the terms of the 16% cases which failed, a lot of them were exceptions. So we broke the code, it's exalted. I'm going to ignore those for the time being, because what I'm interested in is where an error occurred, and I've asked it to percolate out and hit the output. So what I'm interested in here is, does disruption of the code pass through and actually impact output? So there are a lot of cases where something nasty happened, we killed the program dead. There was no need to do anything else. Whereas in these cases, the change actually in some way changed the output. Sometimes disastrously, and sometimes we still got something. So what I'm going to do is I'm going to choose at random 25 of those 37 cases. I'm going to instrument them. I'm going to check the depth of which they've executed. These ones we know the output perfect, the change perfect to the output. These ones it didn't. I'm going to choose 25 here and 25 here. On those, I'm going to insist that the mutation was executed. It did change state locally, and then what depth was it actually executed. So the next graph, those ones are in red. So I've got depth of execution going on the horizontal axis, and up the top is just count. And what I'm arguing is, essentially, there is, in this particular code, somewhere around about 30, depth level of 30, there's a cutoff. And above that, deeper than that depth, most of the mutations cannot be visible. And this, so it should stress, is human ring code. It's not hierarchical. It's full of global data. And essentially, there are data structures to say, here's my picture. You thread, go and execute this part of it. So it's got a lot of global data. Nonetheless, we're still seeing this behavior that deeper stuff tends to have less impact externally.
You say it's human written. I assumed earlier that it was all.
Oh no, sorry. In this second, in the software engineering examples, in the C and C++ examples, those are handwritten. This is from a NASA benchmark. So when they were speccing out their latest supercomputer, they said, from these benchmarks, we want to know how fast your computer is on these tasks.
And so people wrote different concepts of the same things. Different people wrote.
No, I think what actually happened was NASA grabbed things that they were interested in. So that a lot of their benchmark is Fortran code. Some of it is in C, some of it is in other languages. But it was a mix of things that they really wanted to run on their supercomputer.
That's in the premise of my experiment. Because you showed the image should be reproduced, right?
Let me wind back. Yeah. Yeah. So we start with the big image.
Yes.
And the task is produce a thumbnail. And what I'm doing is I'm mutating the source code. And I say, well, with the mutated source code, do I still get the same image?
The source code was written, human written.
Yeah. Okay. Yeah.
In terms of something that I misunderstand function listing, I mean basically function A equals B equals C equals C and that how it counts. Yes.
Oh, in terms of the execution depth. Okay, I didn't explain that.
I mean you have depth of function.
Yeah, so this is compiled using the GNU compiler, and there is a rather nice C utility which will tell you how deep the stack is. So what I did was this is post hoc instrumentation. So I know where the mutation is. I drop a piece of code there that measures how many times that mutation is executed, and simultaneously the execution depth. So this is runtime. So and that's why we get different counts. So some of these suckers will run thousands of times. That individual mutation was run more than 8,000 times in this one. Some of them would run very few times, but a lot of times the mutation was run considerable times. Sometimes always at the same depth, and sometimes over a range of depths, just depending on how the code was written. The last example is much bigger. It's 1 million lines of C++. The point of this graph is just to emphasize there are parts of Gem 5 which are very different. We're going to do the same experiment. We're going to throw 2,500 mutations at the the source code. It's more because this time I didn't try and concentrate the mutations on executed code. So of our 2,500, approximately a half of them ended up in code that's never executed. So I'm excluding those from this table. And what I looked at is the cases where the mutation is compiled, it runs, and produces the correct output. There are quite a surprisingly large number of cases where the mutation occurs, but it's syntactically the same as the original code. So I'm excluding those. Again, a lot of, well, maybe 7% of the time, we actually hit a segment, which seems pretty low. Ones of interest are these 55 cases where we've broken the code, and that the change percolates the output. So Gen 5 has a total of 5 different output files. If we change any of those in any way, then we count it as effect. And then we do the same trick. We choose 25 of those at random and corresponding 25 from the cases where the code is executed. And we're going to instrument them and find out the depth in which they're executed.
Yeah, I just wonder, we can, I'm not familiar with this type, the mutation operator, that's a acceptable short term. If it introduces random changes, and when there's any amount of people who code anything like me and use a bunch of indexes, and then when there's any amount of indexing that gets replaced with random expressions, I would expect cartloads of errors, exceptions.
Yeah,
so maybe it doesn't do that. I mean, so that.
But it doesn't happen.
Yeah.
This was one of the things when we started with GP. We were told very firmly everything is going to break, but it's much worse than that. Most things have no measurable thing. Yeah, so
Do you have examples of what mutations happen? How does it change?
it's a good question. I should have had some on the slides, but I didn't. So Magpie, one of the virtues of Magpie is it works on the syntax at the AST level. So you can do things like replace a statement with another statement. So the syntax should be correct. Occasionally it makes a mistake. But a lot of cases where it fails to compile are not syntax errors, but due to change variables coming out of scope. In terms of the mutations, it has about a dozen of them. So there's some simple things like replace a number by 1 plus that number. Replace a number with a randomly chosen number. Replace a comparison, so a greater than with a less than. So it's always trying to keep syntax, keep the syntax of the original program, just change the semantics in a small way. So that's the goal of Magpie. As you can see, mostly we have a very large fraction which do compile and they do execute. Yeah.
Sorry, by no measurable impact, do you mean the best of the population or all of the?
So here, what we're doing is we have one program, which is the original source of Gen 5, and we're mutating it one time. We run it, see the impact of that mutation, go back to the original source code, mutate it again. So each of our thousands of mutations is independent of all the other ones. So it's not a GA in the sense of having a population. It's a one shot. Let's see what happens.
It's like a single.
Yeah, if you like to think of it like this, but we're guaranteeing that each of our 2,500 is only mutated one time. And as you can see, most of the time the mutations end up in unexecuted code. So it's no surprise that nothing exciting happens. But a surprisingly large number of cases that are actually executed, that execution has no visible external. And again, what we see is, as we look at deeper code, the chances of it having no impact increase. So different programs, different threshold, but maybe everything above about 50 here. If you're deeper than 50 levels in, then at least in these experiments, that mutation doesn't actually change any of the outputs. And I should stress again, this is not a hierarchical piece of code. This is a handmade piece of C++. It's full of objects that have been created and deleted. It's notionally deterministic. You can find examples where it's not. But basically, it's high quality, single-threaded, written by hand. Yet we're still seeing stuff that's deep within the hierarchy doesn't tend to have impact. Yeah.
Have you checked what type of code that's actually produced? Is it just a recursive function or something that just goes down 90 times that doesn't cause any trouble because it's busy doing nothing?
Okay, so I did start analyzing this, and there are some nice examples which you can see. Oh, I know why this did not have any output. In some cases, it's kind of complicated, but there are two, maybe three general causes. One is the change got multiplied by 0. That happens surprisingly often. Remember, this is C++. It's in fairly structured code. A lot of the changes inside a function get stuck inside the function. They change local variables. You pop the stack to go back to call out, the local variables disappear, along with the disruption. And the last one comes to something that was asked earlier. There was one mutation which I analysed in some detail, and I could not understand why it was not beginning. It was executed, it changed several data structures. And it turned out that somebody had written this code, it was executing, it generated this huge pile of output statistics, which were corrupted. But that output statistics were never, that data structure was never written. It was still there. See, I should have stressed, Gen5 is now 10 plus years old. Somebody had written this code, it's still being executed, it still has no impact whatsoever. Whether it's working or not, it has no impact. So this is what happens when you continue with real code. It ain't perfect, and it ain't perfect in many of the ways you would remember from your own program. So the last bit is, well, I hope will be most interesting for you, is what I'm going to claim is this is a general property. If we want to build adaptive systems, then what we need is adaptive systems that are post-Einstein code. I propose that we should do this in terms of maybe having lots of small trees, but maybe other people have better architectures. If we don't have, if we have deep code, then there's a problem that most mutations end up in the deep code. Most of the time, we do not see anything. One possible utility of what we can do in terms of software, I think there's probably in the A-Life community, there is a proof that you can't actually have life in 2 dimensions or pure. All life that we know of is embedded in 3. Software can have as many dimensions as we choose. You can have 3, 4, 5, any number of dimensions. As the number of dimensions increases, then it just becomes easier to connect stuff together. So we may have an advantage over real life here. So what I'm going to argue is, if we don't take precautions, we can end up with a system where it's monolithic. Most of our mutations end up in code which is too deep to actually see that the impact of that whole mutation. So we end up with effectively fossilized code. It may contain many mutations, but those mutations are not being useful. We end up with this sort of ring of out-of-level stuff, which is where we can make mutations that we see, but we're carrying around a lot of fossilized stuff that possibly is not helping us.
Do you actually get that? Will you get no drift at all?
Sorry, can you repeat?
Will you get random drift, or will you get no drift at all?
In the scenario I'm talking about, I think you would get random drift, but random drift is very slow at achieving anything. Of course. Oh, we can still be making mutations, but unless we actually have some external fitness measure, some way of saying whether the mutation is good or not, we end up just as
Like the fitness element.
we end up with just collecting mutations inside the genome, which may not have any.
It's not going to be drift, it's just random.
Yes, sorry, that's better way of putting it. Yes, yeah. And so what I tried to do was argue here we've got a piece of lung tissue. This slide actually has something like a couple of thousand very shallow trees on it. What I've tried to get across is the idea we have some sort of airway, some sort of information highway that links together the shallow trees. So our mutations are on the trees, but in some way we can pass information around. And this is very hand-wavy because I don't know how to do this, but the idea is we want shallow systems rather than having a single monolithic tree. Maybe we want something that's more like mangrove swamp. So mangrove trees are actually interlinked, though individually quite small. We might imagine the tide coming in, bringing a sea of new problems. Tide goes out, takes away a sea of solutions. Maybe as it passes other trees, more calculations are done. But as you can tell, this is more of a hope than anything more substantial. We could look at other biological metaphors, sponges and corals, things that have a high surface area on it. And it don't need to be organic. The pumice or some of the very lightweight minerals as a metaphor for how we might see information flowing between membranes composed of computing elements. So the computing is done on the membrane rather than the membrane providing a separation between parts of the machine. I'm running over, so this is my last slide, really. So what I wanted to summarize is I think it's important in the AI age to stress that GP has been around for a while. It is in use. Evolutionary computation has been used. It can be creative. You'll notice that there is still $10,000 on offer. Well, I ran this GP experiment inspired by the work on biology, and analysis of the results there came to the conclusion that although computing is not reversible, we can use information theory as a way of explaining what happens in the GP. And surprisingly, we see something similar, it's not identical, something similar in real code. From a software engineering point of view, if you want to test code, people do unit tests. And they do unit tests for several reasons. One is just it's easier, there's less resources involved. But there's also, from an information theory point of view, if there's an error in the code, it has less distance to travel before you get to your measuring place. If you do system testing, the error has to percolate through the whole system before you get to the endpoints. So there is an information theory just post hoc justification for doing unit tests. What I've argued in purely hierarchical systems like GP, we see a very strong exponential model. We see something similar in handwritten code. And my last point, I guess, is for the ambitious audience. When we started, we were told very firmly that mutations would just break stuff. It's worse than that. Most of the time, mutations cannot be seen. So I've argued that we need shallow systems where the mutations are visible. Either good or bad, but we need to know what they did. If they're bad, we need to know they're bad. If they're good, we want to hang on to them. The last bit, I'm not sure how familiar people are with Lewis Carroll. So this is Alice with the White Queen. And the White Queen has just said something ridiculous. And Alice says, "Oh, but that's impossible." And the White Queen's response is, "Oh, but my dear, you must practice thinking the impossible. When I was your age, I could think of 6 impossible things before breakfast." So what I'm arguing is, if you want to be ambitious, then you need to tackle things which are currently impossible in the sense of people are just not attempting to do them. If you cast your mind back to the idea of a computer fixing its own bugs, clearly ludicrous. Nobody would ever bother even trying to do that. PhD student was not told it was impossible, went ahead and did it. So today, the argument is not whether a computer can fix its own bugs, but what is the best way of doing it. She forced the door open, and now people are streaming through the doorway. But unless you have the compass to actually kick the door open, then you end up making delta changes rather than creating new stuff. Anyway, I haven't gone on for far too long. Thank you very much.